Yeah, so thanks, thanks to the organizers for inviting me and to you guys. So this is a strange but also really exciting time to be talking about supersymmetry. I think the MSSM is probably the most researched field theory of all time. And it's has a good plurality of attention in terms of LHC searches as well. It's motivated by several things, most notably in our focus for today, the hierarchy problem, also precision unification of gauge couplings at the percent level works a lot better in the MSSM than in just the standard model with no new added matter. That said, we haven't seen evidence for supersymmetry yet. We've seen evidence for a lot of things that aren't generic in supersymmetry. We've seen evidence that the proton is pretty stable. That's not generic in supersymmetry. We've seen evidence that flavor physics is well described by the standard model. Also not generic in supersymmetric extensions. But there are certainly many models of supersymmetry that get around those, that allow totally consistently a stable proton and standard model-like flavor structure. We've seen 125 GeV Higgs. I'll probably talk a little bit more about that. Sort of goes in both columns, the motivation for supersymmetry and the motivation against supersymmetry at the same time. On the one hand, it's a weakly coupled scalar particle that makes this hierarchy problem a lot sharper. On the other hand, the mass is pretty large compared to what you'd expect in supersymmetric theories. So what have we learned so far? I think we have learned decisively that theoretically based expectations for what the most generic supersymmetric theory should look like are wrong. So the question that we're asking isn't the question that SUSY model builders in the last 20, 30 years were asking. What are the nicest supersymmetric models? And are those nicest models consistent with data, and how do you look for them? Instead, the direction has been to say, well, we have LHC data now. It's telling us a lot about the weak scale. And what is it actually telling us quantitatively? What have we learned about the status of supersymmetry? And in particular, how natural can supersymmetry be in light of this data? And so that'll sort of be the theme for the next couple of lectures. Just how natural can SUSY be? And so today, I'm just going to go over some basics of supersymmetrizing the standard model. I'm going to leave the M off the front because I want to presume as little as I can about the model, except that it is supersymmetric and contains the standard model. So SSM works pretty well for that. A little bit of phenomenology and naturalness from the bottom up. And then the plan for tomorrow's lecture is to sort of put this all together and ask, what is the data telling us about whether supersymmetry can be natural, to what extent it can solve the hierarchy problem. So let me see how far I can push this. I could have done harder, but I was afraid of hitting the top, so next time. Oh, I'm supposed to use the stick for that? It's so much less fun. Okay. And then so I won't write putting it all together on the board. You got that. That's for next time anyway. So, okay, the basic hierarchy problem. I know Nima talked about this already. But if you ask about the top radiative corrections to the Higgs mass, and we can just talk about a really simple toy theory. Actually, I'm going to take a Lagrangian that just looks like kinetic terms plus I'm going to have an h t left T right. I'm not even going to gauge any symmetries, just some scalar, which I'll call H. And then I'll add in, that has a Yukawa coupling YT. And then I'll add in some lambda I H squared S squared. And first we'll think about these S's as being very heavy. I'll be moving the scale of the S mass around, so let me add some MS squared, SI squared. Okay, so there's a couple of different scalars. So this top part, it contributes a loop integral. If you just do this loop integral, you have a d4k. You have two propagators. So you have two k squared denominators. Then you've got a trace of a sort of k dot sigma bar. I'm going to work basically in file notation through these lectures. You have a minus sign because it's a fermion loop. And this ends up giving, and you have your Yukawa coupling squared. So this ends up giving you a contribution that looks like lambda squared over 8 pi squared times cutoff squared. No other scale to the problem. It's a massless fermion to delta to the renormalization of that H mass. If I were to also look with a minus sign coming from that fermion loop, if I were to also look, so we'd say, well, is this physical or not, right? I'm sure you have seen this before, and probably even with Nima in the last couple of days. Is this physical or not? Depends. And clearly, if you write it in dim reg, you're not going to get any cutoff dependence. But if you add some new scalar to your theory, some heavy scalar near the cutoff, so a heavy mass, then you know that this integral associated with that scalar loop is going to have a k squared plus ms squared. And so in addition, same 2 pi's and a lambda s. Sorry for the notation. I guess I called this guy y. And this is going to go like a lambda over 16 pi squared times cutoff squared plus a correction that goes like ms squared times a log. And this log you would certainly see in any regulator. And this is a log, if I continue working here, it's a log ms over lambda. So when we talk about using a cutoff regulator, seeing a quadratic divergence, what that really is, it's shorthand for UV sensitivity. For sensitivity to any new physics that might come up at energies much higher than the weak scale, say new scalars coupled to the Higgs or coupled to the top, or new fermions, have any interactions with them, those will generate radiative corrections to the Higgs mass. If you know the specific model, you can calculate them. But if you don't know the specific model, you can't calculate them. That's the sensitivity to unknown physics that worries us. That's the essence of the hierarchy problem. Now you can also see, if I now imagine taking this scalar loop and think about the scalar as being light rather than heavy, say close-ish to the weak scale, still have this exact same form. And you can already see the potential for a cancellation of these two corrections to the Higgs mass, right? If there was some symmetry that related the couplings of scalars, these quartic couplings, to the squares of the fermion interactions, that symmetry would allow for the lambda squareds to cancel. And again, the cancellation of the lambda squareds is a good proxy, a good hint that this is no longer sensitive to what physics you put at high mass scales. So it removes the deep UV sensitivity. Why do I say deep UV? I say deep UV sensitivity because, of course, this theory has our sort of toy standard model up to some mass scale ms. And then I have my S plus standard model. And then I have my cutoff. But this is also a cutoff for the standard model, right? The mass of it, below ms, this theory is just the standard model. It's sensitive to the physics at the scale ms. We know exactly what it is, I put it in. But even when you cancel the quadratic divergence, you still have that ms squared sensitivity in the Higgs mass. And now it's calculable. You know exactly what it is. You can't get rid of it. It's just an intrinsic smaller amount of tuning in the theory. Okay, so this is sort of a little toy model of what we're going to see in supersymmetrizing the standard model. But it has all the essential ingredients. New scalars with symmetry-related couplings. They solve the hierarchy problem. Yeah?
So you said when you set lambda equals to 2y squared, you won't have this quadratic divergence, so you're not sensitive to far UV physics. But then if I add another heavy scalar, the mass is
right.
still going to be corrected by this.
No, so that's a very good point. So if I just supersymmetrized the standard model and then coupled it to non-supersymmetric physics at high energies, I would still have a hierarchy problem. I would still get corrections from that very high energy physics. But if supersymmetry were a symmetry of that whole theory, then you can show in general that any supersymmetric additions at high scales are not going to reintroduce quadratic divergences, even if they have large masses. So thank you for bringing that up. So we have cancellation of quadratic divergences, but the very theory that we introduce to solve these quadratic divergence problems is also introducing its own radiative corrections at the scale ms to the Higgs mass. That's why when people originally started talking about theories of supersymmetry, the way the story went was, well, we have lots of supersymmetric partners. Okay? Some of them, if your supersymmetry is broken at a high scale, there's a lot of running that controls their different masses. A bunch of partners. Typically, the strongly interacting partners end up on the heavier side of the spectrum. And it's the top partner, among others, that's controlling the radiative corrections to the Higgs mass, to the VEV of the Higgs. That means that whatever's setting the mass of the Z should also put it somewhere up here near the top of the spectrum. And that's sort of the original vision, the way that you would most want supersymmetry to work, is with the Z near-ish the top of the spectrum. And this is why LEP was a very exciting machine as well, because there was lots of promise to discover superpartners. But now that neither LEP nor the LHC has seen any such thing yet, there's a possibility to really ask much less. See, this is very much motivated by, well, what model would I want to write down if I were God? What would the supersymmetric world look like? And now we can ask the better question, which is, if we don't know what kind of models God would actually prefer, what are we learning about nature? So I think this is, as far as exploring supersymmetry, we're exploring supersymmetry with the LHC at a level way beyond what could have been done before. And that is quite exciting. That's why I'm excited to be talking to you guys about supersymmetry today. All right, so enough of the small stuff. Let's supersymmetrize the standard model. So just for conventions, we've got, I'll use lowercase fields, but I need maybe more space. Okay, I'll just do this. I'll squeeze it a little bit, sorry. So we've got force. So these are going to be left-handed spinners to represent the left-handed spinners to represent the left-handed antiquarks and the left-handed positron, respectively. So these fields create left-handed positrons and antiquarks. So these are in the anti-fundamentals of SU3. Doublets and singlets, and then charge a sixth. And then we also have the Higgs, continuing my table over here for lack of space, which is a singlet, doublet, and I'll work with a charge plus 1/2 Higgs doublet. I'm also going to try to distinguish the Higgs doublets from just the neutral part of the Higgs by using capital H for the doublet, but I will probably be inconsistent about that, so apologies in advance. So these are all the left-handed fermions plus one scalar in the standard model. Now supersymmetry is a symmetry whose generator is fermionic. It's generated by Q alpha and its conjugate, Q dagger alpha dot. So this is a left-handed spinner. It's an SU2 left index. This is right-handed. Their anti-commutator is going to be something like a -2 times a sigma matrix times the momentum generator. All the other commutators, QQ, QP, etc., all vanish. And now if you ask, what representations does this algebra have? Let's say I had a representation that contained one scalar state with Q dagger alpha dot on my scalar state equals 0. Okay, so then Q's are going to act like, so this is the lowest rank state, and then Q's acting on this will generate other states. So I've got S, that's a scalar. I have to also have in my theory then the state Q alpha S. I know this can't be 0. Now, there's two alphas, so these are really two states. And they should be fermionic states because I built them by acting with a Q. So there's two fermionic states. And I know they can't be 0 because if I acted with Q dagger on this, and then I wrote down the commutator of Q dagger and Q acting on S, that has to be non-zero as long as S has a non-zero momentum. But Q dagger annihilates S, so it had better be that Q dagger acting on this state is non-zero. And so this has to be a non-zero, and there's two fermionic states. And then I can also put together a Q alpha, Q beta S. And then you might ask, well, this looks like it has two left-handed spinor indices. But actually, because these Q's commute with each other, anti-commute with each other, that forces that the only index structure this could have, it has to be proportional to epsilon alpha beta. So I should say this is equal to some epsilon alpha beta times S prime, where S prime is my one new scalar state. So this is one scalar. So all in all, two scalar, two fermion states. And I can't go any further because if I were to act with Q dagger on these, I would just get back some of the lower states. And if I were to act with another Q, I'd have a square of a Q, which is 0, since they're fermionic operators. So those are the states, 2 scalars and 2 fermions. Now things start getting, and I should say, a good part of the SUSY phenomenology you can get just from thinking about those 2 states. But there's some crucial pieces, absolutely crucial pieces, for which you actually need to learn more. And the easiest way is by trying to translate this into a field description. So how am I going to talk about 2 scalar states? I add a complex field phi, scalar field phi. Now, if I ask how many degrees of freedom does that have, how many components, it has 2 real components. But if I ask about phase space, right, so considering the phis and the pi's, well, I have a phi, I have a pi, which is equal to phi dot, and then I have the complex conjugates, so that's 4 phase space components. Now, how about my 2 fermionic states? I can encode those in a Weyl fermion, psi alpha. Now, this has, if I just talk about field components, this has 4 because it's a spinor with 2 complex components. So that's 4 real components. So you can see these degrees of freedom counting no longer match up. So how does that jive with what I had up there? Well, at the phase space level, they still match up. Because when I ask what are the pi's here, I have my 4 psi alphas. And then the pi alpha are just equal to psi dagger sigma naught alpha. So this is not independent of the psi components. Call that 0 phase space components. So at the level of phase space, they still match up. But at the level of field components, they no longer do. And this tells you that when you write down a Lagrangian in terms of phi and psi, say the simplest free Lagrangian for the scalar and the fermion, you can work out supersymmetry action on those fields that closes on the support of the equations of motion, but doesn't close off the support of the equations of motion. To close SUSY off the equations of motion, you need to introduce another field that has 2 degrees of freedom, but doesn't actually have add anything non-trivial to the phase space. And so this is done by just having an auxiliary field, F, also scalar, but with no time derivatives. So that means that you could just solve for F in terms of the other fields, reduce it away. And the simplest supersymmetry invariant action that you could write down is just a kinetic term for phi, a kinetic term for psi, plus an F star F term. And then on the equations of motion, the equation of motion, for this free theory, the equation of motion for F is just F equals 0. It's trivial and you don't really need to think about it. But when you start adding interactions to this supersymmetric theory, they will involve F. And those are actually very important. In fact, the way we get that quartic interaction that solves the hierarchy problem is from the interactions of the F, effectively from integrating out the F in the scalar potential. Okay, once we have these, I don't really want to, I mean, there's some really nice structure in supersymmetric Lagrangians in superspace and so forth, but I don't want to spend too much time on on motivating it and going through it during the lecture, because I want to get to these questions of naturalness and SUSY phenomenology. So I'm just going to state a lot of things. Actually, before I do that, I wanted to go back just to our standard model field content. Now that we have this field language for talking about for talking about supersymmetric particle content. I can supersymmetrize these, I can group all of these matter fields into supersymmetric multiplets. You all know how this goes. In addition to that, you could just group the quark, that's a Weyl fermion, with a scalar, complex scalar, the squark, left-handed squark, of the same gauge quantum numbers, U conjugate with its own scalar, D conjugate with its own scalar, and so on. And then the Higgs with a Higgsino, and this time the Higgs is the scalar, the Higgsino is the fermion. In addition, we have to put the gauge fields into multiplets, and it works similarly. The Bino gets paired with, sorry, the B, the hypercharged gauge boson, gets paired with a gaugino, Majorana fermion, W with a Wino, and the gluon with a gluino. And so this is the basic matter content, almost. This is the matter content that you would need just to symmetrize the matter content of the standard model. Now, I say almost. Why? Well, over here I've just added scalars. Over here I've added fermions, but they're real representations of the gauge groups. Here I've added one chiral fermion. And what do we have to worry about when we add chiral fermions to a theory? Anomalies, right. So this is technically has made our theory anomalous. So, and it's not a big representation where you could have some intricate cancellation of other degrees of freedom cancel. I mean, well, you could have other degrees of freedom cancel its anomalies. The simplest thing to do would be to just make this a vector-like representation. And we'll motivate that from other directions as well. But so far, just at the level of supersymmetrizing the matter content, this is what we get. We've noted that there's an anomaly. And we'll have to come back and fix it at some point. Let me get a little bit more space up here. So I suspect that many of you are already familiar with superspace, and so I just want to give a sort of bare bones introduction to those who aren't, and hopefully that will be clear enough. So superspace is by far the easiest way of making sure that a Lagrangian that you build is actually supersymmetric. I could just write down my component fields, phi, psi, and f, and write down SUSY transformations of them and check term by term. That gets quite labor-intensive when you have this many fields. And superspace just helps you write down manifestly supersymmetric theories, and then talk about in the most general possible form. So we take our coordinate x mu, and we're going to add to it two Grossman spinor-valued coordinates, theta, theta dagger, just complex conjugates of each other. And now you can realize that commutation relation of the q's by defining q alpha to be a dd theta alpha So there's a theta derivative, and there's a spatial derivative multiplied by theta dagger. Now note, because these are Grossman, so I want to assign dimensions to this. I'm thinking of it as a space-time object, and here I have a derivative, so I'd better assign consistent dimensions. So The only way these two can work out is if theta has mass dimension 1/2, dd theta has mass dimension -1/2, del mu, sorry, I wanted it the other way around. No, that's, yeah, del mu has mass dimension 1, so that should have -1/2 and +1/2. And then, because these are Grossman variables, you end up with this sort of weird integral d theta is just the same as a differentiation. So I'm just going to say that dd theta have mass dimension +1/2, and theta has mass dimension -1/2. Okay? Now, you can write fields that depend on x, theta, and theta dagger. And there's a way of getting a field that has exactly this content, the phi, the psi, and the s. The way of getting that is by just deposing a differential operator that annihilates this. So if I restrict to that condition, where this d alpha dagger looks something like it has also an I dd theta dagger term and a sigma theta del mu. Okay, I'm trying to be very schematic here. I'm not even off the top of my head sure what the right sign is, but there's a differential operator, d, that's a natural operator to define in this space. It's natural in the sense, in part, that it sort of acts like a differentiation with respect to theta. But if you just did dd theta, that wouldn't commute with q alpha, right? Because q alpha has thetas in it. It's a dd theta plus a correction that makes it commute with all the q's and q daggers. Okay? So in fact, let me just write it as plus ... because I'm really not going to use the detailed properties of D. If you impose this condition on a field, then it turns out that you can always write psi as a phi of another variable I'll call y, a psi and an f of y. Okay, you can break down, and these are exactly the components that we wanted over there. So imposing this differential operator condition on phi, which will play an important role again in another place too, gives you a field that carries exactly the information you want to represent one of these fundamental scalar and fermion degrees of freedom, so-called chiral multiplet. So this is called the chiral superfield. And then in the case of vectors, we can just, instead of imposing this, just impose a reality condition on the field in x, theta, and theta dagger. And that reality condition gives you a field whose physical degrees of freedom are the vector and the gauge boson and the gauge GNO. Sorry, I'm going to try to rearrange the boards a little bit, but I'll bring everything back, I promise. Now what have I done? So y, by the way, I didn't define it, and it'll be in my lecture notes. There's a lot more on this stuff in my lecture notes that I'm actually going over. Y is defined as a linear combination of x plus a theta dagger theta term, such that when you expand it, out, that big capital phi in terms of components in terms of x. So y, I will write it out actually, because otherwise I think this will be a little bit confusing. So y is just x mu plus a theta dagger sigma mu theta term. And that means that if I were to expand out phi in terms of functions of x, I'm just Taylor expanding the little phi at this argument. It's going to give me lots of some spatial derivatives. So that when I write this in terms of phi of x, I would have a phi of x plus first derivative term del mu phi of x plus a box phi of x term. And then similarly for the psi and for the f. Now, I don't want to, this series, this expansion in theta of the terms involving phi, that truncates, okay? If I did another, because the next term in the Taylor's expansion involves the square of the same Grossman variable. This, whenever I write theta squared, this is really a theta alpha, theta beta, epsilon alpha beta. So that doesn't vanish. But if I multiplied in another theta, either one, I would always get 0, since these are Grossman. So then I have plus the psi terms, plus theta squared f. So how can I use these fields to build Lagrangians? That was my claim, is that this technology, which I am hopefully summarizing coherently, its claim to fame is that it makes it very easy to write down supersymmetric Lagrangians. So let's do that. So one thing that's supersymmetry invariant is just if I take, let me write down an action. If I take an integral over all these variables of any function of x theta and theta dagger. This is supersymmetry invariant because if I ask how does q act on it, q is just built out of a theta derivative and an x derivative. And so inside, q acting on this would just be an integral of a total derivative. Okay, so this is invariant. It turns out that if I ask about something like this, with just a theta integral, not a theta dagger integral, this is also invariant, and I better add its complex conjugate to keep things real. This is also SUSY invariant. It's clearly invariant for exactly the same reasons under Q, but it's not obviously going to be invariant under Q dagger. This is invariant under Q dagger if and only if this d alpha dot operator that I alluded to earlier, the one that commutes with del theta and del theta dot, acting on W equals 0. Well, what is d alpha dot going to annihilate? It's going to annihilate any product of phi's that are annihilated by d alpha dot, but it's not going to annihilate phi stars, right? So this means W can be built out of phi's, basically nothing else. There are also terms that you can build out of the specific terms that you can build out of the gauge multiplets that have invariant integrals of this form. Now we can just do some simple dimension counting, right? We want our action to be dimensionless. That is mass dimension minus 4. Theta had mass dimension, integral d theta had mass dimension 1/2, so this whole thing has 4 of those. It has mass dimension 2. S has to have mass dimension 2. If I'm building S out of fields, the only renormalizable thing I can write down is a sum of phi star phi's. And I can always choose a basis for my fields where this is diagonal. So it's that plus non-renormalizable terms you can add down, which will all be suppressed by cutoff mass scale to some power. And if you just had this and nothing else in your theory, this doesn't look like much, right? Let's say I have one chiral field phi, okay, and let's say there's some global charge or gauge charge that it's charged under. So then I have to be not only supersymmetry invariant, but invariant under that charge. So I can write down this S. And then over here, I can only write down products of phi's, not phi stars. So I'll never get anything. I can never build anything that's neutral under that global charge. So W would just have to be 0 if I had one chiral field. So my whole Lagrangian is just this term. Well, although this doesn't look very dynamical, when you expand it out, when you account for all these derivative terms in the expansion of phi, this actually just gives you, this is the superspace notation for the simplest action that I wrote over here. The free scalar, the free fermion, and the completely uninteresting square of the auxiliary field. Okay, that's the simplest theory. Now notice, in that case, so one charged psi, that means one charged scalar and one charged Weyl fermion. My Weyl fermion, I'd say, oh, its mass is protected by a chiral symmetry, right? Because there's no invariant mass term that I can write down when it's charged. The scalar, usually we don't say the scalar's mass is protected by any symmetry at all. But I've just written down the most general supersymmetric Lagrangian for that theory. And I told you this doesn't have a mass scale in it. You know, even if you don't believe that I've expanded it correctly, there's no place that a mass term could possibly come from in this Lagrangian. So the scalar's masslessness is being enforced too. What's happening is that you simultaneously have SUSY that's enforcing m phi equals m psi, and then a chiral symmetry that's imposing m psi equals 0. So this is the first example of how a scalar's mass can be protected by supersymmetry. All right, now let's see. I am going to quickly have to learn how to use half blackboards better. So now what I want to do is just write down the allowed, so this is everything as far as supersymmetric Lagrangian. This is where all the kinetic terms come from. At the renormalizable level, this is all I can write down for this S term, which, by the way, this is also often denoted, called the D term, and denoted that way. And sometimes this one you'll see denoted as it's a lot more compact than writing integrals. It's called the F term. It's related to the role that these will play in setting the values for these auxiliary fields, for the auxiliary field F. Okay, I can still pull down this superspace board. I just want to write down the interactions now of a supersymmetric standard model and then see how they play out in components. But first, I'll do just a generic version without the details of the. No, I'll just go directly to the standard model, actually. So what kinds of terms can I have in the superpotential? It has to be built out of products of these phi fields. And yeah, this W is also called the superpotential. And it has to have mass dimension 3 by the same counting as above. So I can have if I had some singlets, which I don't in the standard model, I could have some linear terms. I'm going to forget about those. We don't have any singlets, at least not yet. I could write down terms of the mass dimension 1 parameter that involve some psi I, psi j, and I can write down terms, trilinear terms, okay, let me start with these. What can I write down in the standard model of this form? And remember, I'm allowed to use the Higgs doublet, but not the Higgs star. So I can write down H, Q, U conjugate with some Y up. And that's the only Yukawa coupling with a Higgs type of thing that I can write down. I can write down couplings L, Q, D conjugate as well. These now would have a Yukawa coupling between the selectrons, say, and the quarks. These have a brand new flavor structure, and I'll come back to these later. You can also write down these. I think that's the usual convention. I can write down these, but I don't want to. I'm going to actually set those to 0 right now. One can enforce a parity called R parity that forces those coefficients to vanish. So I will set them to 0 for now. I want to go back and add, oh boy, why did I put it up there? I want to add another Higgs doublet, which means more lifting. To cancel the anomaly of my earlier Higgs, and to give myself another thing to write Yukawa couplings out of. So I'll call this H up, because it couples to the up quarks. And I'll also add down-type Higgs doublet with charge -0.5. Now my Higgsino content is anomaly-free. And now I can write down the rest of the interactions that I wanted. So this guy I've relabeled H up, H down, Q, D conjugate, and an H down, L, E conjugate. I can write down two terms of this type, mu H up, H down, plus some mu prime H up L, I can always choose a definition of do a redefinition of fields, since the lepton doublet and the H down doublet actually have the same gauge quantum numbers. I can always do a field redefinition to make this go away, perhaps at the cost of reintroducing these, or the same symmetry that I used to suppress these would also forbid this interaction, same R parity. So this is the superpotential that I'll keep, is just these terms. And now when you ask what interactions does this give, remember, we can just think about expanding out each one of these fields into components and select terms with two powers of theta. So the simplest way is, say, over here, I can take 1 power of theta from one field, 1 power of theta from another field. That piece of the interaction will look like a Higgs scalar QU conjugate, just a normal standard model Yukawa. I could have also done it the other way. So there's these other Yukawas related by supersymmetry, say Higgsino, quark. And then there will also be terms where both thetas, there will be terms where both thetas come from the same superfield, right? So it's really the F piece of, say, U conjugate. So I end up with terms H up squark, both scalar pieces, FU conjugate. And then, when I go back to integrate out the F's, remember I also had from the kinetic term, I also had an FF star. This is going to give me a scalar potential that's just dW d psi I mod squared. It's worth actually working this out in some simple examples to convince yourself that this is the case. But if you haven't gone through it before, but in order to get a supersymmetric theory with interactions of the Yukawa type, you also necessarily get this type of 4-valent scalar interaction. And so this, for example, in this case would give us a quartic interaction, squark, H up. We also have 4 squark vertices and so on. These are never of direct phenomenological interest when you're talking about decay of a superpartner, say. This kind of quartic interaction is never relevant. What it is relevant for is you'll notice that this is exactly going to come in with a coefficient of y up squared. And if I close that squark, those 2 squark legs up with a loop, it's exactly the term that we saw in our earlier, when we were working out the mechanics of how scalars cancel the quadratic divergences. This is exactly going to give us this loop that we wanted to cancel the top quadratic divergence. So these are critical, not for understanding what SUSY does at colliders, but they are critical to the consistency and the way, the magic of what the theory does. Now, there's 2 things that we're missing at this point from this, well, 3 things that we're missing, I guess, 3 major things. So I haven't added gauge interactions yet, and I haven't added supersymmetry breaking. But I want to emphasize something that comes along with without gauge interactions and without SUSY breaking, there's something else that's missing from this theory. So we talked about quartic interactions. And if you look so where are quartic interactions important in the standard model? We have 1 quartic interaction in the standard model. It's the Higgs quartic. If you look, the quartics here are never going to produce a Higgs quartic because you have no terms that you can write down in the superpotential that have two Higgs bosons, two Higgs superfields in them. So there's nothing that when you differentiate and square is going to give you 4 Higgses. This gives us Higgs masses, but there's nothing in here that gives a Higgs potential. Now I could add a scalar to my theory. If there was an additional scalar, then I could add, for example, a lambda h up, h down s, and then that would give a Higgs quartic. But in the minimal supersymmetric standard model, there's no room for a Higgs quartic at this level. So where does phi to the 4th come from? It can come from something like this. That's one option. Not in the minimal standard model. It inevitably comes from gauge interactions, which I'll get to in a moment. And it can come at loop level. This is a tree level effect. And at loop level comes from SUSY breaking. This term, the gauge interaction term, as we'll get to in just a second, only ever gives a quartic the same size as the Higgs Z coupling. And that means that the Higgs mass from just this term is always strictly less than the Z mass. Okay, because it's just being set by the same gauge interactions as the Z mass. And then the algebra works out that it's strictly less. So since we've measured the Higgs of the Z masses and we know that MH is not less than MZ, we know something like this kind of interaction or some loop level in physics has to be important to the Higgs sector if supersymmetry is correct. I think that was suspected to basically probably be true after LEP and the Tevatron, but there was still the possibility that the Higgs might be lighter and just decay differently. Now we know what the Higgs mass is, and it's absolutely clear. If supersymmetry is the theory of nature, you need either large radiative corrections from SUSY breaking or some pretty significantly coupled additional fields that give rise to a larger Higgs quartic. That gauge term just isn't enough to explain the physics of the Higgs that we see. Okay, so I've done the superpotential. I'll just summarize what the whole interaction potential is now, and I'll write down the gauge terms too. So we have these Yukawas, which I can just write down. In general, as a psi I psi j plus Hermitian conjugate. These are the matter Yukawas that I get. It's sort of not surprising, right? With these, it wasn't surprising that since supersymmetry is relating bosons and fermions, once you have this Yukawa, you'd have to have this Yukawa. Likewise, it shouldn't be that surprising that once you have, say, a hypercharge coupling, you also need to have a coupling where you replace one of these fermions with its bosonic partner and the gauge boson with its fermionic partner. Shouldn't be surprising that there have to be gaugino Yukawas associated too. And those always take the form the gauge coupling times something that looks, so here lambda A is the notation I'll use for the gauge bosons. These are the gaugino Yukawas. And then finally there's the scalar potential, which has two parts. There's these f squareds, which I can write as f squared plus a half dA squared, just like these F's are the auxiliary fields of the phi's, of the chiral multiplets, and we can completely solve for them in terms of other fields. The D's are the auxiliary fields of the gauge multiplets, and we can completely solve for them in terms of other fields. The FI's are just equal to dW d phi I, and the dA's are equal to GA. Basically a combination dependent on the charge of the squares of all the bosonic fields. And now, this, you see, can give rise to a quartic coupling, right? In fact, because now we have dA is going to have terms quadratic in each of the Higgses, each of the Higgs fields. And when we square it, we will end up with a particular combination. It's in terms of just the zero components. It'll end up being that in the D, and then squared with a G squared over 8. There's actually a G1 squared plus G2 squared up here. That's a part of the D term. Okay, just for reference of where the Higgs quartic couplings are coming from. So that's the Lagrangian without SUSY breaking. Now there's just really quickly break supersymmetry here. So Bill, just to summarize, what are the sort of key additions relative to the standard model? So we've added new partners. We've doubled the particle content. That's a pretty big, major addition. We've added new Yukawa interactions, and it's mainly these new Yukawa interactions that are going to control the decays of superpartners. And those are the ones that are just mnemonically trivial to remember. So if you see a superpartner spectrum, unless there's very intricate mixing effects, and sometimes there are, you have very little excuse for not being able to estimate how the different superpartners decay, because it's all trilinear couplings. Sometimes you have to sew them together, but it's all trilinear couplings that are closely related to the standard model couplings you know and love. In addition, the big, more subtle changes are in the Higgs sector. You added a new Higgs doublet, and the self-coupling has this significantly restricted form, because you can't write down general potential interactions involving scalars. They have to descend from these chiral interactions. And that's quite a restrictive constraint, unless you add new matter content. Okay, so the old way of talking about soft SUSY breaking is just the sort of naive one. Well, if I add masses to some particles, but they're of a scale m, right, then energy is much above m. You shouldn't care whether they're massive or massless. Anything dimensionful that I am isn't going to change, that I add isn't going to change the viability of supersymmetry as a solution to the hierarchy problem. And that can be made rigorous by actually carefully checking what happens in those cases. But there's a much nicer, more modern way of thinking about breaking. So, and that's just to think of soft SUSY breaking as adding SUSY breaking sporions. So for example, I can add a field X that takes a VEV, say it's standard model neutral, that has a VEV. I don't really use this first VEV, but in general I should allow VEVs for both the scalar component of X and the auxiliary field. Once I get an Fx, which breaks SUSY, then when I write down terms like d squared theta, d squared theta dagger, dagger x, phi dagger phi. This has dimension 4. And this S is supposed to have dimension 2, so I better add a 1 over mass squared. If I take x to its vev, I'm going to get a term that looks like fx squared over m squared. Remember, fx had mass dimension 2, so this whole thing has mass dimension 2, times phi dagger, times phi star phi, sorry, don't know what that is, times phi star phi. So this is just the term where I take the theta squared. Every term in this integral comes from expanding this out and picking out terms with 2 thetas and 2 theta daggers. Well, if I look at the terms with 2 thetas in x, 2 theta daggers in x dagger, and no thetas in the phi's, that's going to give me this fx squared over m squared times phi star phi. So that's phi masses. And similarly, I can start adding x's, not x daggers, multiplied by phi's in the superpotential in W. So if I add things like x phi, well, I'll just do it explicitly, and x h up, h down, that's going to go with a 1 over m. That's going to go to an fx over m. Sorry, that's dimensionless, no 1 over m, just an fx times h up, h down. This is another type of mass term for the Higgses. And if I had something trilinear, it would give me a dimension 1 coupling. Phi I, phi j, phi k, some coefficient a, which is equal to f over m, okay, times some coupling. Hope that's clear. So these are called A terms. This is called a B term. These are the 3 types of things that you can get by just adding in spurions, taking them to their vevs. Scalar masses, these chiral scalar masses, the B terms, and and trilinear couplings of the scalars with a dimensional coefficient. That's what you get when you break SUSY, and because I can think of this all as coming from a spontaneous breaking in a scale m, it's unsurprising that by this fx, it's unsurprising that this essentially guarantees that it descends from a wholly supersymmetric high-scale theory where all the usual arguments should protect the Higgs mass for radiative corrections larger than the scale of these coefficients, the B and A coefficients, and the masses. And that's indeed true. But as I mentioned at the very beginning, now we have a mass scale where we add a lot of new particles. That's a cutoff to the standard model. There is some fine-tuning of the Higgs mass just from the radiative corrections associated with these soft masses. Okay, so now we want to calculate radiative corrections to the Higgs mass within SUSY. And I think I will sacrifice the standard model board for this purpose. So the question is, how do we quantify? I already mentioned this picture. This is sort of the and we'll see as we go where this comes from. But if I assume nothing about where this superparticle spectrum comes from, where that scale, where that symmetry was actually spontaneously broken, what the scale of fx and m is. If I assume essentially nothing about that, what can I say about fine-tuning of the Higgs mass? And well, maybe there's there's one very zeroth order thing to say even before I talk about fine-tuning quantitatively, which is just that at least within the context of the MSSM, the Higgs potential is really, really heavily constrained, right? I've got this quartic term that I mentioned. Has a flat direction, and it has a quartic direction. And then there's two terms I'm just writing down the potential for the zero, for the neutral components. There's a similar one for H down. And then there's this B, H up, H down term that also came from soft supersymmetry breaking. It's worth mentioning that this is a supersymmetric parameter, and all the other mass coefficients here are SUSY breaking parameters. And there has to be already a little magic just to get these of comparable sizes, but that's by no means impossible. That quartic, it has a flat direction. In order to keep the vacuum from running away to infinity, it had better be that the mass squared in that flat direction is greater than 0. But in order to get electroweak symmetry breaking at all, the minimum eigenvalue of the mass squared matrix has to be less than 0. We simultaneously have those two conditions. These can be written as conditions on the parameters. Which I won't use their detailed form, but just want to emphasize that even getting electroweak symmetry breaking is a pretty non-trivial requirement here. It's not obvious that you'd get viable electroweak symmetry breaking for all parameters. You only get them for certain cases. Also, because this quartic is set by the G's, in the MSSM, the mass of the Higgs is strictly less than or equal to at tree level mz times cos 2 beta, where tan beta is defined to be the ratio of the up-type Higgs vev to the down-type Higgs vev. Okay, so in general, if you want to get Higgs greater than or equal to 125 GeV, you need either loop level effects from the stop. This is things like that, among other diagrams. That gives you a Higgs quartic. You don't get any correction in the supersymmetric limit to the Higgs quartic, but you do get corrections in the SUSY breaking limit. They're big enough to get your Higgs up there. Roughly speaking, if your stops are heavier than 1 to 2 TeV, or you have something like the singlet that I mentioned up there, any other various significantly, near strongly interacting sort of order 1 coupling additions of more beyond the standard model physics near the TeV scale, which I will just call shouldn't call it BSSM, that sounds derogatory, BMSSM. I think, at least I first heard that term from one of Scott's papers. So the Higgs potential is a significant constraint already on minimal supersymmetric models. We should be thinking it means either supersymmetry isn't a theory of nature, or stops are heavy, or supersymmetry is the theory of nature, stops are light, but the standard model plus just the minimal additions isn't a big enough theory. We really need some significant new interactions that could alter the collider pheno as well. But I want to put that aside because this problem is quite MSSM specific. You can't derive a bound very easily on the stop mass if you allow for other possible new physics. I want to just ask the question, what's nature telling us about the fine-tuning of the Higgs in the context of supersymmetry? So I think the sharpest and best defined version of the question is if when the LHC turns on at 13 TeV, supersymmetry just pops out in some of the first analyses, and that's still possible, what would we say about SUSY based on what we learn about the superpartners there? And then the second, much tougher, slimier, squishier version of the question that's really harder to nail down is based on the null results that we see now, what can we say about the hierarchy problem in the context of SUSY? Okay, is it possible to turn absence of evidence, of course, with a theory with a free dimensional parameter that could go up anywhere between the weak scale and the Planck scale, it's essentially impossible to turn absence of evidence into evidence of absence. There will always be a higher mass scale that you can think about. But we can at least try to turn absence of evidence into evidence of fine-tuning. Okay? And that would be interesting. And the basic relation that this draws on is just that in the standard model, in the MSSM, to a good approximation, you can relate the z mass squared. And the exact coefficients here depend on tan beta and stuff like that. But this is the right order of magnitude. Plus mh up squared. This must be a Freudian. No, I really don't. I actually like BMSSM stuff. I don't know why I'm writing it as BS all the time. There's this basic relation. It's roughly true. And here, what we haven't seen, it's really hard to constrain without assuming large tan beta. It's hard to constrain the sort of heavier Higgs boson masses. So we don't really have robust limits on that directly. But we do get a handle on what mu is from Higgsino masses, and in particular Higgsino mass bounds for now. And here, we can't measure it, but we know that this gets radiative corrections from stop, etc. If there were no radiative corrections, then we'd have nothing to worry about in terms of the hierarchy problem. But because there are, we also get radiative corrections to these soft masses from other soft masses. So one can define a rough notion of tuning. Okay, and this is Kitano and Nomura's tuning parameter. And a lot of this discussion I'm taking from a recent paper by Papucci, Josh Ruderman, and Andy Weiler. You could define a tuning parameter in terms of any given particle superpartners contribution to the Higgs mass squared divided by mh squared over 2. Okay, and this 2 is sort of related to the fact that the mass of the excitation about the VEV is always related by a factor of 2 to the bare mass about the origin. But clearly, you know, there's certain ambiguities about this formula, right? When I talk about whether a theory is 5% fine-tuned or 10% fine-tuned, you should, of course, know that if I changed my denominator from mh to mz, or got rid of the over 2, I'd change my answer by about a factor of 2 doing either of those things. So we shouldn't get hung up about 5% versus 10%, but we should certainly care what the scale of this fine-tuning is. Right? It's telling us something different if we discovered supersymmetry in a regime where these deltas are sort of order a few, or if they're order 1,000. If we found at a future high-energy collider superpartners with 10 TeV masses and concluded that the sensitivity of that the Higgs mass had this delta parameter of order 1,000, or 10 to the 4, that would mean that there was some significant fine-tuning. Whatever supersymmetry is doing for the hierarchy problem, there's still some significant fine-tuning going on in the universe to get the standard model out as we see, and to get the weak scale as we see it out. So trying to quantify bounds on this delta without getting too hung up about factors of 2 is a useful way to think about this question I asked. How natural can supersymmetry be, and what are the null results telling us about nature? So the first kind of delta you can look at, the contribution from the Higgsino, that's pretty straightforward. Mu is just getting added directly into here. And so if you asked, what's a delta, or what kind of mu would give you a 20% tuning, you'd say if mu is 200 GeV, that corresponds to a roughly 20% tuning. And then the tuning goes like the square of mu. So if mu is 300 GeV, this tuning gets roughly a factor of 2 worse. If you're getting up to 500 GeV mu's, then you're really talking about a few percent rather than tens of percent fine-tuning. Now there's radiative pieces as well. Okay, so now we can ask, well, what about if mu enters directly at tree level? There's a lot of other particles that enter in at loop level. The stop contribution, for example, if you look at delta mh up squared from the stop, that ends up, you've got a color factor of 3, y top squared. And then you have some combination of soft masses and A terms times the usual log of the cutoff scale. Roughly, I'm just going to say cutoff scale over TeV. Okay, where this cutoff is wherever the soft masses were generated, that's the ratio of scales over which these stop soft masses in the A term are going to be able to contribute to running of MH up. Now, sometimes, certainly in the early days, it was particularly interesting to think about lambda being a rather high scale. SUSY breaking generated, say, some intermediate scale roughly in between the weak scale and the Planck scale. And then this log could be pretty big. It can be order 10. But at the bare minimum, we should be talking about lambdas factors of 10, tens of TeV, hundreds of TeV. Okay? It's not, you can't have SUSY breaking being mediated to the standard model at just the scale of the soft masses without also seeing some additional effects. There should be some separation of scales. And at least this log greater than or equal to, around 3 seems pretty reasonable. And if you use a log of 3, then we'd find that, let's see, roughly m stop squared, or really the sum of the two stop masses squared, should be, if you want to have some given fine-tuning delta, you should have that mass minus a half, around 600 GeV, times then that gets, sorry, minus a half. That gets more to be a more severe constraint the larger that log gets. Now this is for the top, right? The stop, because the top has a large Yukawa coupling, induces very big radiative corrections. If you asked about, say, the bottom quark, then the bounds are going to be weaker on that mass by a factor of y top over y bottom, which is like a good factor of almost 2 orders of magnitude, right? And 60 TeV isn't that severe of a constraint. The W is another example, slightly stronger coupling than the B, but still, when you work out the one-loop contributions from the W radiative corrections, you just find that M2 should be less than about 900 GeV times the same delta dependence. Sorry, I think I called that the mass of the W, but hopefully you all knew that I meant the mass of the we know. And for a weakly interacting particle, lower weak production cross sections, this isn't a constraint that we have any direct handle on at the LHC. Actually, the most direct constraint we have is the 2-loop, is a constraint that arises at 2-loop on the gluino mass. And it actually sort of works in tandem with the stop constraint in an interesting way, as this is what we'll talk about tomorrow. The gluino only affects the running of the Higgs mass at 2-loop, and you have a relatively short scale over which to run, so you might think that that can't be such a large effect. But between large color factors and the fact that G3 and Y top are both big, this is also pretty substantial. This is again around 900 GeV for those same parameters. With now a higher power of the log, of course, because it's a 2-loop effect. So it depends more strongly on how far you're running. Now notice that if we were talking about, say, intermediate scale, so 10 to the 11 GeV, this log would be about 20. And then the bound you'd get on the gluino by the same argument would be much tighter than the one on the stop, around 300 GeV. And this is already what the kind of mass scale that the Tevatron was probing. For this log when the log is large, say larger than about 6, this gluino bound is actually more stringent than the bound on the stop. So what are these telling us? Well, this is giving us the language in which to ask the question, what fine-tuning is necessary to accommodate supersymmetry with existing data? To actually answer that question, we can't just write the equations. We have to sort of put these next to, try to mesh them with the constraints on supersymmetry and all the different channels that the LHC is looking at. So that's what I wanted to talk about tomorrow. Just to conclude, a few wrap-up remarks for today's lecture. So fine-tuning in supersymmetry I should emphasize, it's not like the LHC turned on and we woke up and freaked out about fine-tuning. It's been an old concern. It was already the LEP paradox concern about fine-tuning before I even entered the field. That was mainly a concern about fine-tuning in high-scale SUSY mediation, where these logs are big and the masses really should be very light. Because the logs are so big, you really end up with order one couplings of order one effects of one soft mass on any other soft mass. And so we really expected the whole spectrum to be, well, accessible at LEP. Not we, that wasn't me, but I wasn't around then. But we as a collective field. But what recent results have done, what the LHC has let us do, is probe this in a much less model-dependent way. To ask the question, how much tuning is forced upon us regardless of whether the scale of mediation is high or low, regardless of what kind of texture of soft masses you end up with as a result of funny RG running in between scale of SUSY breaking and the weak scale, and regardless of where that scale of SUSY breaking is. On the one hand, we have the discovery of the Higgs, which is really pointing towards either heavy stops, and that, if you just compare those numbers to these numbers, those stop masses imply a pretty hefty degree of tuning. Or some new beyond the standard model, beyond BMSSM physics controlling the Higgs sector. That second possibility, I think, is especially interesting because it would feed into changing the way that superpartners decay and perhaps changing how we interpret the LHC bounds. But it's really now. It's really not even 2 years ago, certainly not 10 years ago at LEP, but now that the LHC is really probing this sort of 10-ish, 20-ish% fine-tuning range where if you see something, you'd say, well, I don't know. That could have just lined up that way. You know, sometimes I learned yesterday in another context that 3 log 2 over 2 is remarkably close to 1. Don't ask me, that's a long story. It's like 1.04. So sometimes little accidents like that happen. But it's this round of LHC searches that are going to tell us whether we're in that range, or really supersymmetry as an explanation of the big hierarchy problem has to introduce some little tuning as well, which would be certainly telling you something, I think, still ambiguous until you actually find some positive evidence, but something pretty exciting and interesting about nature. So I'll stop there, take any questions, and I guess we can talk more this afternoon as well.